The key to whether or not this device can amplify power is the lift-to-drag ratio of the airfoils and what is achievable. Assume we design airfoils with a lift-to-drag ratio of 10:1, which means we have 10 units of lift and 1 unit of drag at some RPM of the Blue motors. Now, assume it is possible to redesign the airfoils so they have a lift-to-drag ratio of 11, which means we have 11 units of lift and 1 unit of drag. If we can do that, the Blue motors need to consume the same amount of power to overcome the drag in both cases. However, in the second case, the lift has been increased by 1 unit. The increased lift causes the torque on the output shaft to be increased by 1 unit. Whenever the torque on the output shaft is increased, the RPM of the output shaft will also increase until the drag is equal to the torque. The power generated by the output shaft is equal to the torque on the output shaft times its RPM, so whenever the lift of the airfoil is increased, the power generated by the output shaft also increases. If it was possible to repeatedly redesign the airfoils to get more lift with each redesign without increasing the drag, then we would eventually come to a point where the power generated by the output shaft would be greater than the power consumed by the Blue motors to spin the airfoils. Therefore, the lift-to-drag ratio of the airfoils is the key as to whether or not this device is capable of amplifying power. This graph illustrates what is theoretically possible. If we repeatedly design airfoils with higher and higher lift-to-drag ratios, there will come a point where the output power will be greater than the input power, since the input power is constant and the output power is continually increasing as the lift-to-drag ratio is increasing. Whether or not this is achievable in practice is unknown.